Before analyzing the motion of the bowler, we first define a coordinate system. The horizontal direction along the pitch is our x-axis, and the vertical direction is the y-axis. At the beginning of the run-up, the bowler starts from rest. His initial velocity is 0. But in the next few seconds, powerful forces generated by his legs will accelerate his body forward. To begin running, the bowler pushes his foot backward against the ground. According to Newton's third law, the ground pushes back with an equal and opposite force called the ground reaction force. This forward force is what propels the bowler toward the crease. At the same time, gravity pulls the bowler downward with a force equal to his weight, while the ground provides a normal force supporting his body. But the bowler cannot accelerate without friction. Static friction between the shoe and the pitch prevents the foot from slipping. This frictional force provides the necessary grip that allows the bowler to push against the ground and convert muscular effort into forward motion. The magnitude of this frictional force depends on the coefficient of friction and the normal force between the shoe and the pitch. Now, the net force acting on the bowler produces acceleration. According to Newton's second law, force is equal to mass multiplied by acceleration. When the forward force exceeds opposing forces, the bowler accelerates toward the batsman. The center of mass of the bowler moves forward as his speed increases with every stride. As the bowler continues the run-up, his velocity increases steadily. This increase in velocity can be described by the equation velocity equals initial velocity plus acceleration multiplied by time. Since the bowler started from rest, his speed grows rapidly as he approaches the crease. Each stride adds more forward motion, building the speed required for a powerful delivery. With increasing velocity, the bowler's momentum also increases. Momentum is defined as mass multiplied by velocity. The faster the bowler runs, the greater his momentum becomes. This momentum is crucial because it will soon be transferred through the arm to the cricket ball during the delivery. As the bowler reaches the crease with maximum momentum, his arm begins its rapid rotational motion. In physics, this motion can be described as circular motion, where the shoulder acts as the pivot point. The rotating arm has an angular velocity, which determines how fast the arm sweeps through space. The ball at the end of the arm follows a circular path around the shoulder, gaining speed as the arm rotates. At every point along the circular path, the ball possesses a tangential velocity. This velocity is always directed tangent to the circular path and perpendicular to the radius of rotation. The magnitude of this velocity depends on two factors: the length of the arm and the angular velocity of the rotation. The faster the arm rotates, the greater the tangential velocity of the ball. At the precise moment of release, the ball leaves the bowler's fingers with a high initial velocity. The direction of this velocity determines the release angle, which plays a crucial role in the ball's trajectory. From this moment onward, the ball is no longer constrained by the arm and begins moving freely through the air. To analyze the motion of the ball, we decompose the initial velocity into two components. The horizontal component determines how fast the ball travels toward the batsman along the pitch. The vertical component determines how the ball rises or falls during its flight. Together, these components completely describe the motion of the ball immediately after release. Once released, the cricket ball becomes a projectile. The only significant force acting on the ball is gravity, which constantly pulls it downward. While the horizontal velocity remains nearly constant, the vertical velocity gradually decreases due to gravitational acceleration. As a result, the ball follows a smooth parabolic trajectory toward the batsman. Now the ball is traveling rapidly toward the batsman. In the next stage, we will analyze the full projectile motion of the ball and observe how gravity shapes its flight path across the pitch. The moment the ball leaves the bowler's hand, it begins moving freely through the air. At this point, the ball behaves as a projectile. Its motion is determined by two factors: the initial velocity given by the bowler and the constant pull of gravity acting downward. As a result, the ball follows a curved path known as a parabolic trajectory across the pitch. At every instant during its flight, the ball possesses a tangential velocity that is tangent to its path of motion. This instantaneous velocity continuously changes direction as the ball travels along the curved trajectory. While the magnitude of the velocity may vary slightly, its direction always aligns with the direction of motion at that precise moment. Throughout the entire flight, gravity acts on the ball with a constant downward acceleration. This gravitational force gradually reduces the upward component of the ball's velocity while leaving the horizontal component largely unchanged. Because of this continuous downward acceleration, the ball's path bends smoothly toward the ground. The total time the ball spends in the air is known as the time of flight. This duration depends on the initial speed of the ball and the angle at which it was released. Using the principles of projectile motion, we can calculate exactly how long the ball remains airborne before reaching the batsman. While gravity influences the vertical motion of the ball, its horizontal motion remains nearly constant. This steady horizontal velocity carries the ball rapidly toward the batsman. The horizontal distance traveled during this time can be calculated using the horizontal component of the ball's initial velocity. Within just over a second, the ball reaches the batsman at remarkable speed. What happens next occurs in only a few thousandths of a second, the collision between the bat and the ball. In the next stage, we will analyze the physics of this impact and the enormous forces involved. In less than a second, the cricket ball travels from the bowler to the batsman. At this moment, the ball carries significant linear momentum, which depends on its mass and velocity. The batsman prepares to strike, positioning the bat so that it meets the incoming ball at the perfect moment. The collision between the bat and the ball happens extremely quickly, lasting only a few thousandths of a second. During this brief interval, the ball compresses slightly against the surface of the bat. The bat exerts a very large force on the ball, reversing its direction and dramatically increasing its speed. The change in momentum of the ball during this collision is described by the concept of impulse. Impulse is equal to the force applied multiplied by the time interval of the collision. Even though the contact time is extremely short, the force involved is enormous, producing a large change in the ball's momentum. Before the collision, the ball's momentum is directed toward the batsman. After the impact, the bat transfers momentum to the ball, sending it rapidly away in a completely new direction. This transfer of momentum is what propels the ball high into the air toward the boundary. As the ball leaves the bat, it now possesses a new velocity and a new launch angle. These two factors determine the future path of the ball through the air. From this moment onward, the ball once again behaves as a projectile, moving under the influence of gravity alone. The initial velocity imparted by the bat determines how far and how high the ball will travel. As the ball rises through the air, gravity continuously slows its upward motion. Eventually, the vertical component of the velocity becomes zero. This point marks the maximum height of the shot, the highest point reached during the ball's flight. After reaching its peak, the ball begins to descend. Now gravity accelerates the ball downward, increasing its vertical speed as it falls. The horizontal component of the velocity remains nearly constant, allowing the ball to continue moving forward toward the boundary. The total time the ball remains in the air is known as the time of flight. This duration depends on the initial speed of the ball and the angle at which it was released. By applying the equations of projectile motion, we can determine precisely how long the ball stays airborne. The horizontal distance traveled by the ball is called the range of the projectile. This range depends on the initial velocity, the launch angle, and the acceleration due to gravity. In this case, the powerful strike sends the ball far beyond the boundary rope, a spectacular 6. From the bowler's accelerating run-up to the rotational motion of the arm, from projectile motion across the pitch to the powerful collision with the bat, every moment of this cricket shot is governed by the fundamental laws of physics. What appears to be a simple sporting action is in reality a remarkable demonstration of mechanics in motion.